Welcome dear viewers. In this video we are going to discuss 1's complement and 2's complement of a binary number. If you recall, in the previous video we discussed about the r's complement, and r's complement of a number is given as r is power n minus the number in the base r, and n here is the number of digits that are present in the number n. In the similar fashion we can define the r minus 1's complement as r is power n minus 1 minus the number in the base r. If you observe and look the similarities between two equations, there is only one dissimilarity, that is we have subtracted 1 here. Therefore, what we can essentially find out is that r's complement is equal to r minus 1's complement plus 1. For this video, we will restrict our discussion for r is equal to 2, that is binary number system. Therefore, 2's complement of a binary number can be given as 2 raised power n minus the number in the binary system, and 1's complement can be given as 2 raised power n minus 1 minus the number in binary system. Consider the example where we have to find out the 1's complement of 10110, and we can see that n here is 6. Therefore, 1's complement of this binary number will be equal to 2 raised power 6 minus 1 minus this binary number. And you can see the second term is in binary number system, and the first term has to be also in binary system to do the subtraction process. Now we can find out 2 raised power 6 will be equal to 1, and there will be 6 zeros after 1 in the binary number system, and we have to subtract to minus 1 to get the first term. So this will yield 6 ones. So to find out the 1's complement, we have to subtract the given number. So what we can get here is that 1 minus 1 is 0, 1 minus 0 is 1, 0, 0, 1, and 0. You can observe that the given number was this, and this is its r's complement. It is like we have switched 1 to 0, 0 to 1. So in a nutshell, what we can conclude that 1's complement of a binary number can be obtained by changing 1 with 0 and 0 with 1 in the process of finding the 1's complement. The range of 1's complement can be given as 2 raised power n minus 1 minus 1 to minus 2 raised power n minus 1 minus 1. So this is the range of binary numbers that can be represented if we have n digits using 1's complement representation. So talking about the 2's complement, so 2's complement is equal to 1's complement plus 1. So if we talk of this example, that is 101101, so it is 1's complement was equal to 010010. To get the 2's complement, we have to add 1 to this, and this will be equal to 0, 1, 0, 0, 1, and 1. The direct method would be we have to obtain 1 from the LSB, and after that we have to switch every 1 to the 0 and every 0 to the 1. So directly we have to keep this 1 as it is, and then we have to keep switching the bits. So 0 for 1, so 0, 0, 1, and 0. You see both are equal. If we take another example wherein we have to find out the 2's complement of this given number, so by this shortcut method we have to find out the first one from the LSB. That means we have to keep the bits as such, and whenever we find the first one, we have to also keep that as such, and then we have to just replace the 0 by 1 and 1 by 0. We can cross check this. We have given number as 1, 0, 1, 0, 0, 0, and it is 1's complement will be 1, 1, 1, 0, 1, and 0, and we have to add 1 to get the 2's complement. 1 plus 1 is 0 with the 1 carry, so 1 plus 1 is 0 with the 1 carry, 1 plus 1 is 0 with the 1 carry, so it is 1, 1, and 0. So you can see that this result is same as that of this result. The range of 2's complement representation of number is from plus 2 raised power n minus 1 minus 1 to minus 2 raised power n minus 1. For example, if n is equal to 4, we can represent the range of numbers from 2 raised power 3 minus 1 to minus 2 raised power 3, that is equal to 7 to minus 8 can be represented using 4 digits. Now if we talk same range in case of the 1's complement, this will be from 7 to -7. In previous video, we have discussed that complement representation of number is always used along with the sign representation. That is, we also use sign bits first, then we take complements of that number. Now, one important point to mention is that in 2's complement representation of a binary number, if we have 1 as a sign bit, and after this sign bit, all of the bits are 0, 0, zeros, and we have n such zeros after that, the number will be equal to minus 2 raised power n. For example, if we have 1 and then we have 3 zeros, the number will be equal to minus 2 raised power 3, that is equal to minus 8. As the sign bit is 1, it means the number is negative, which is consistent with our result. And if we take the 2's complement of this whole number, which will be equal to 0, 0, 0, and 1, this will be 2's complement representation of this, and this is equal to 8. So the strength will be 8. Now, if we take another example wherein we have 1, 0, 0, 0, so the number will be equal to minus 2 raised power 4, that is minus 60. Another important point to mention in 2's complement representation of number is that if we have a number, say minus 5, you know how we represent minus 5 in the 2's complement representation. We first write positive 5, and positive 5 can be represented by 0 as a MSB. Then we have representation of 5, that is 101. Now minus 5 is represented as 2's complement representation of this number, that will be equal to 1, 1, 0, and 1. Now you can see we have negative sign, that is 1 as the sign bit, and this implies negative. And if we take 2's complement of this number, it will be equal to 1, 0, 1, and 0, which means that the number is minus 5. So minus 5 is represented as 1, 0, 1, and 1. Now if we extend and we have one extra 1 in front of this most significant bit, you can see the result remains same. So most significant bit is 1, it implies the number is negative. And if we take the 2's complement of this, so it will become 1, 0, 1, 0, and 0, which is equal to 5. So result again is minus 5. Similarly, we can extend any number of 1's in front of this most significant bit, and this will be still minus 5. Now here we have taken the 4 binary bits and all the possible combinations from 0, 0, 0 to 1, 1, 1. So in unsigned number representation, this will be equivalent to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Now in signed representation, 0 at the MSB position represents positive number. So up to this, we will have positive numbers, and after this, we will have negative number. So in signed representation, this will be 0, then plus 1, plus 2, plus 3, plus 4, plus 5, plus 6, and plus 7. And after that, you can see that most significant bit is 1, that means minus 0, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, and minus 7. Now talking about the 1's complement representation of number, so you see that again the most significant bit is 0, so it means positive number. And so we will have positive 0 here, plus 1, plus 2, plus 3, plus 4, plus 5, plus 6, and plus 7. As I have told you that the positive values, that is positive numbers, have same representation in complement form. That is, again here we will have plus 0, 1, 2, 3, 4, 5, 6, and 7. So positive numbers in binary form and complement and their complement representation, there is no difference. However, when it comes to the negative part, so now the most significant bit is negative. It means the number is negative, and its strength is in 1's complement form. So it will be minus, and if you take the 1's complement of 0, 0, 0, so it will be minus 7 here, minus 6, minus 5, minus 4, minus 3, minus 2, minus 1. And if you take the 1's complement of 111, so it will be minus 0. You see that we have positive 0 and negative 0 in 1's complement representation of number. Now if we talk about the 2's complement representation of number, so again the most significant bit is negative, so the number is in 2's complement form. And if we take 2's complement of this number, it will be again 1, 0, 0, 0, that will be 8. So the number is -8, then the number will be -7, -6, -5, -4, -3, -2, and -1. So there is only one unique representation of 0 here. And here you need to be very cautious that if the most significant bit is 1, and if all the rest of the bits are zeros, it means that the number is -2 raised power n, where n is the number of zeros in the magnitude part. This is all for now. Thank you.